All right, on to the next example. So you have a whole bunch of forces acting on an object here. So this one's, it's going to turn out to be easier than the first two examples, but just to show you, you can deal with however many forces you want. It's not that hard to find the resulting force. The resulting force is if everyone's pulling on this object as they are, what direction is the resulting force going to be? So you can do this however you want. You can label each vector if you want. So you can call it vector A, B, C, and D, and E. All right, and keep with that fashion. So you can do A plus B plus C plus D plus E. People who took physics, you'll have a little bit of an advantage here because you'll do the shortcut. And people who didn't take the physics are going to look at this and see the shortcut, so it doesn't matter to me. So if we look at vector A, it doesn't have anything in the x direction, but it's straight up, so 25j. The B vector would have a positive I direction, no j. The C vector would be negative 4i. And again, all these vectors have either x or y, so there's going to be a lot of zeros in here as well. So D has no I, it's pointing down, so that'll be negative 6j. And E, 0i minus 30j. So now, because it's addition on the one side here, that means we just got to run through and deal with the signs inside. So we end up with 0 plus 12, which is 12. Take away 4 is 8. So we end up with 8i. And the j's, 25 plus 0 plus 0, still 25. Minus 6, minus 30, so let's take away 36. So it's negative 11j. So there we go. We want to determine the resulting force. So that means we need to know what this is saying is find magnitude and find direction. So we just now go back to our magnitude formula. So 8 squared plus the negative 11 squared. Whoops, I don't need that square root sign. And calculating that, so 8 squared, 11 squared, square rooted, about 13.6 units. Theta, tan inverse, y over x. Again, we're going to ignore the negative, and we'll use it to interpret final answer. 11 divided by 8, tan, 50, let's call that 54 degrees. So therefore, the resultant vector after all these people are pulling on the object, R is 13.6 units. According to this, positive 8, so that's going to be going to the right or east. Negative 11, so down or south. And it's going to be a rotation of 54 degrees. So there is a simple example like that. All right, I want to quickly talk about velocity as a vector. So there's a couple questions dealing with this. Velocity is a measure of speed, which is magnitude and direction. So it's a vector because it has both magnitude and direction. And what we run into is something called relative velocity. All right, relative velocity. So we're going to fill out this chart, and you can see I have bus, train, and car. So we're going to have the bus doing 80 kilometers an hour. We'll have the train doing 100 kilometers an hour. And we'll have the car doing 120 kilometers an hour. And we're going to do 3 locations. So we'll go side of road. We're going to go in the right order here, bus, train, and car. So this is where you are located. So if you're at the side of the road, how do you see the bus? So when you're watching the bus, you're going to see that it's doing 80 kilometers an hour, and it's going to be to the right, because that's the direction the arrowhead's pointing. So that's how you view it. So you're standing at the side of the road, so you're going to find the first line here is as per normal. So left, in the car, it's 120 kilometers per hour to the right. Nothing new either. Okay, if you're on the bus, so we're going to just cross out the diagonal from that point. So if you're on the bus now, and you meet you're at the front of the bus and you meet the train, how fast does it look like the train is going? Well, our brain is kind of wired to put everything in kind of perspective here. So when you are focused on just the train, your brain says that the train is coming at you and you are stationary. So that's how the brain kind of interprets data for you. So if I had everything sort of painted out and all you could see was the train, your brain would tell you that the train is doing 180 kilometers an hour and it would be going to the left, okay, coming straight at you. Okay, so that's how your brain interprets or translates that information. It doesn't see the train doing 100 kilometers an hour. When you meet cars, you always think, holy cow, they're going really, really fast. But you got to remember, you are doing a certain speed as well. So for example, bus and car meeting. If you're sitting in the bus and you look out the window, the car looks like it's just barely passing you. So it looks like the car is really only doing 40 kilometers an hour to the right. And that is because if the bus is doing 80, so if the bus is doing 80 and the car is doing 120 in the same direction, that means the car is going faster. But when you look out the window and look at the car, it just looks like the car is going a little bit faster than you, and you interpret yourself as not moving. So it really looks like it's doing 40 kilometers per hour. So it's that relative velocity. How do you view things? So now if you're on the train and you're looking at the bus, same thing. You see the bus as doing 180 kilometers per hour, but it's in the opposite direction because now you're in the train, you're facing to the left, so you see the bus going right. With the car, so the train and the car going opposite directions, you actually view the car doing 220 kilometers an hour to the right. So it's that whole perspective thing. So when you see that car, you think the car is doing an amazing speed, but you got to remember you're also doing a particular velocity. So that's that 100 plus 120. So now if you're in the car and you drive past the bus, it looks like the bus is actually backing up. And it's true, that's how your brain kind of visualizes it. If it doesn't have any landscape around it, you've probably come up to an intersection before where you see a vehicle beside you start moving, and then you have that sensation that it's actually you moving, and you push hard on the brake. Okay? If you can't see the terrain around you or reference points, you have a hard time putting in perspective who's actually moving at the intersection. So it's the same thing here. As the car goes by, if you are staring out the window straight at the bus, it actually looks like the bus is backing up at 40 kilometers an hour. So that would be to the left. And it's funny how your brain interprets things. And when the car and the train meet, it's the same thing. If you can't see the landscape around you and you just see the train out the window, it's going to look like it's doing 220 kilometers per hour to the left. Okay? And it's not actually doing that, but that's how our brain is interpreting the information as it comes to us. So that leads us to this formula here, relative motion equation. All you need to understand is the formula itself. So relative motion, so VREL is just what is, and I'll just say, keep it simple, what is apparently happening. All right, so if you're looking out the car window and you see the bus, you're passing the bus, it looks like the bus is backing up. So that's VREL. VA is your velocity under normal circumstances or normal conditions. So under normal conditions. So that's just saying no wind, no current, depending on if you're in a boat. And then VB is factors influencing motion. And I got to keep it fairly generic because there's a whole bunch. So this could be wind. It could be current if we're in a boat. And we'll run across a couple. So on your cheat sheet, you do need to have that formula right there for the exam and test purposes. And maybe just a brief description to remind you what exactly are you dealing with. Okay? So a couple of examples that we'll work our way through. Maybe we'll just do the one example and you can see the other one's very, very similar. A plane's traveling 400 kilometers an hour north, 60 degrees east. Okay, so I'm going to give myself XY axes. So north, 60 degrees east, that means I've turned and that's where my 60 degrees is. Keep in mind, this is not the angle we want. All right, you always want the angle with the x-axis, so it's the 30 degrees. So switch those right away and cross out the one you don't want. The pilot set a course of 500 kilometers north, 30 degrees east. So when the pilot took off, this is where he planned on going. All right. He has 30 degrees there. So the angle we want is 60 degrees. Determine the velocity of the wind. So what's happened? He's taken and pointed it in the direction of the green. He wanted to go this way, or that's the way he pointed. He is now doing this direction, so if you're on the ground, so that means that there must be some kind of wind vector that's pushing on him. So remember that the formula we talked about, V relative equals VA plus VB. VB is the wind. Okay, so that's what we're trying to find, is the wind vector. So that means we've got to rearrange this equation and get VB by itself. So it's going to be V relative minus VA. So when you're looking at the original equation then, or sorry, the original situation, oops, our formula says that we want to take V relative. So what is V relative here? V relative is what you see the plane doing. VA is what the pilot wanted to do. And then VB is that wind factor. Okay, and you can use wind as a variable. It doesn't, the VA, VB is kind of generic. I keep it simple. So relative is what was viewed. So that's the 400 cos 30. So this is an observer on the ground, says, I see the plane doing this. The pilot, though, because the plane isn't going to bend, the wind doesn't bend its direction, it just pushes it. So the pilot is sitting in the airplane thinking that he's pointing in this direction, the 500 cos 60 I plus the 500 sine 60J. All right, so the wind is influencing the plane. How much is it influencing it? Here's the formula down here that we decided on. So we need to have subtraction. So if we do the subtraction then, so 400 cos 30, 30 cos minus 500 cos 60. So I get 96 I, and the other one, 400 times 30 sine minus 560 sine at negative 233 J. So if I want to find the magnitude of the wind, we're going through that same process that we have been. And this example has the wind doing 252 kilometers an hour. So for some bizarre reason, this plane is flying into a extremely terrible storm, because 252 is freaking strong wind. Not recommended flying conditions. So let's continue on with the crazy pilot here. So when we get the angle divided by 96, shift tan, so 60, let's call it 68 degrees. So that wind is just coming in and screaming. So the wind is 252 kilometers an hour. So pilot and crew probably going to end up dead if they're flying in a storm like that. Direction, again, you're looking at your original vectors. The 96 is positive, so you were heading east. Y component's negative, so you're going to be bending south, and it's 68 degrees. So now you have a direction for your wind. So that is what the wind is, or how it's influencing the plane. Now I do have another example. You can try that on your own if you want. Here's the homework. Yeah, it's a large chunk. This is normally would have been a full-day lesson, 2-day work period, so give yourself the time frame to get through this. The only difference with this particular example that I'm not doing is it's in water, so you're on a boat rather than watching an airplane. So give those questions a try, and as problems develop, make sure you ask for some help. Good luck.